We began to discuss last time various forms of the variational principles, and basically the logic was that we say we want to describe some physical situation. We assume that there is a certain symmetry. So, for instance, the case which we dealt with was Einstein saying that I assume that there is space-time is Lorentz invariant under rotation with imaginary angles, as we saw. And then this you postulate, and then you can check whether it agrees with experience or not. But then you have to, then you introduce another axiom that our dynamical systems are described with the variational principles. So the equations of motion will follow from this relation where S is some functional. And the logic is that we have to find this functional based on symmetry, and we saw that, for instance, when we're looking for the action invariant under Lorentz transformation, we got the action which is we also wrote it that we derived it from writing it down in this form. It's far from obvious that it is Lorentz invariant, because Lorentz symmetry mixes x and t. However, we derived it. We started with another form, which is much more in which Lorentz symmetry is obvious. This is the form when you take dt ds square minus dx ds square over ds. So in this case, these two forms correspond to two ways of describing curves. You can either say that, for example, when you have a curve, you have y and x coordinate, you can either say, let's fix the function, or you can say, let's look at the parametric representation of this curve, namely y is y of s, x is x of s, where s is an arbitrary parameter. And we actually can, this action was unique. It was unique for the following reason. We just say that that it is if we take t imaginary or x imaginary, it should be usual invariance under rotation in four-dimensional space. By the way, we already discussed this question. How many rotations are in 4 dimensions? In 3 dimensions, there are 3 independent rotations. And remember how many rotations there are in 4 dimensions. There are 6 rotations because you can we talked about it. 1, 2, 1. We describe rotations by fixing the plane in which you rotate, and there are and the plane is fixed by 2 indices and antisymmetric with respect to each other. I'm saying this. I'm reminding this because what can you say about Lorentz transformation? How many independent parameters are there? So count the number of parameters of the most general Lorentz transformation. What are they? Exactly, and this 6, of course, is the same 6 which were angles of rotation in 4-dimensional space. It's just precisely the same 6 parameters. This action is invariant actually under the group, not simply under Lorentz group, but under the group of translation, which makes it a 10-parameter group. Sometimes this group of transformation, which involves rotation and translation, is called the Poincaré group. So this is invariant under Poincaré. That's one thing. And it is also invariant, we said, under reparameterization, because when you change S to f of S, how the quick way, of course you have to make the substitution. I shall not be, I will just remind you what we did. We say let's take a new x, which is x of f of S, plug it in, everything cancels, and so the action for x tilde is precisely the same as the action for S, for x. Now, quick way to see this thing is just to notice that you have one differential in the numerator, ds, and here you have ds square, but you have a square root, so ds and ds cancels here. That's why basically this is invariant under reparameterization. One should be careful with such logic when you have higher derivatives, but at this point it's more or less precise. Okay, and we also said that we derived this action. I derived it by taking dt ds out of the square root last time, and then we get this thing. There is a slightly more general way which we will need, is just to say let's choose the parameterization when the parameter is precisely S. You see, when you have this general parameterization, you can always choose it so that f is the inverse function of t. So we choose t equal to s, and x is a function of s, which in the terminology is that in this case it's people call it choosing the gauge. When you choose the gauge, you obviously get this gives you 1, this gives you velocity, and you have relativistic Lagrange function. There's one question here. Remember, we defined energy of a system also by making reparameterizations. We said that translation invariance in S, translation invariance in time, better to say, is related to conservation of energy. We constructed the functional which is conserved when the system moves. It's also called integral of motion. It's an integral of motion, conserved quantity. Now, suppose I want to write down here. There is a symmetry here, obvious symmetry. What should we do and suppose I want to extract conserved quantity related to this symmetry. We already saw that each symmetry of the action corresponds to conservation. So what should I do? We did it several times already. How to, when this is straightforward to check that this is indeed symmetric, but if I want conserved quantities, what's the general prescription? Remember the general prescription I discussed. What? Yes. And okay, so we want to make, instead of making symmetry, we want a general rule. I repeat it again and again because it's important. Is to take infinitesimal transformation which depends on the parameter. Now, tell me what the energy is in this case. What will be the answer? You can. It doesn't require any calculation. It just requires some thinking, and the answer is slightly surprising. So, suppose I will make this change of variables. And I want to, the general rule was, I remind you, you make gauged transformation, and the variation of the action should be something multiplied by a dot ds. And this something is precisely the conserved quantity which we are looking for. So what would happen if I plug this in back into this action? Just try to take the hint that it's not related to calculation, it might be. Well, you can calculate, of course. Remember how we did the calculation. We called this f of s, and then we plug it to the non-relativistic action and derived the energy and so on and so forth. Here I already said at the beginning the result of this calculation. What happens if I plug in this action these modified values, with f of s? I was just at the beginning telling you it's ds here, everything goes away. So what's the answer?
Nothing.
Nothing changes. How would you? What is your conserved quantity?
Would be the whole thing.
Wait a second. You started in the right direction, but then deflected a little bit. So I want to find thing which is in the bracket. What is? I'm asking actually the question. What is standing in the bracket?
Would that be nothing?
There would be nothing, yes. Energy which you get is zero, identically. Actually, some people say that invention of zero in early mathematics was one of the greatest steps mathematician did. So we have zero because it's parametrically invariant. So when you choose this thing, you get nothing. Well, how to interpret this? I actually will say that's, if you probably heard or even know to some extent, theory of general relativity, theory of gravity by Einstein. And in this theory, This theory is very similar to, this is just a toy model to the big Einstein theory, in the sense that Einstein theory is derived by requiring that coordinates, that there is a symmetry under general coordinate transformation. So it's four-dimensional generalization of here we have one parameter reparametrization, here we have four parameters, and the Einstein action actually that's the logic is precisely as here. We're just looking for the action invariant under this symmetry, and because of this the total energy in the Einstein action is identically zero. Now, that should puzzle you, because you certainly know that there was a Big Bang, that the universe expanding, cooling off, so energy is not zero, but it's moreover it's going down. How would you answer to this? In the first place, it seems that how would you answer the puzzle that Big Bang seems not to conserve energy? So do we have conservation of energy after all, or not?
Can we say the Big Bang shouldn't have happened?
Well, that's a little extreme. Well, I would not forbid myself thinking about such things, but anyway, the answer to this, like the answer here, is that when you have Big Bang, there's the energy or temperature we're talking about is the temperature of matter. There is also gravity. When you take together energy of gravity and energy of matter, it remains zero. Okay, but there is one unclear question here, that okay, but we know that at least in non-relativistic limit we do have energy. So how shall we find it? How shall we find energy from this? What we got here apparently is not energy, it's zero. And we have to understand this, why it happened, and what to do, how to find. It's physically obvious that if we had conserved energy in non-relativistic case, we also should have it in relativistic case. I will give you a hint. The hint is that symmetry responsible for physical energy is not this symmetry, it is something else. So which symmetry, and now I'm asking you, which symmetry is responsible for, when you look at this action, which symmetry is responsible for physical energy? The answer is simple and natural. It's not something complicated at all. Just look at this action and think, what should we do with it? What kind of symmetry is responsible? It's certainly not symmetry S plus A, but what else do we have? What? What? A time reflection. Well, we need infinitesimal symmetries. What I'm talking about is we have obviously the symmetry of the time translation. So far, I was discussing parameter translation, now we have also a different symmetry, t to t plus a, and let's see what it gives. It's actually quite simple, dt ds square. So variation of the action will be proportional to we have to vary this thing. We have 1 divided by square root dt ds square minus dx ds square. And here on the top we have dt ds, d delta t ds.
Why doesn't that give the same, because the first S equals equation uses T as the
Very good point. You see, we impose the condition. Here we do not impose any condition or any gauge condition on T of S. It's general. If you do impose it, we will impose it, but after we consider the variation. We allow, when we perform the variation, we vary only this action. And then at the end, we can choose parametrization. If you, the point of the matter is that the symmetry which we will be dealing with, it will require simultaneous change of S and T. So you will see, so far I'm just basically the one of the rule of thumb is that don't fix the gauge prematurely. You will pay dearly for that. And many wrong papers are written because of this. Okay, so let's just do the variation. You see that we got the since delta t is this, we get the variation of the action, which is proportional to dt ds square root multiplied by a prime of s ds. And now we can fix we fix the gauge after we performed the variation. These operations do not commute. So we have T of S equal to S, it's convenient gauge. And we immediately see that the energy, which is coefficient in front, is proportional. Well, the proportionality coefficient is just the mass, square root of 1 minus v square. The square root here, when t is equal s, becomes velocity, and that's the famous E equal mc square expression, which follows from relativistic theory. And the coefficient here, actually, of course, symmetry consideration don't fix the coefficient here. The coefficient is fixed by comparison with non-relativistic case. When non-relativistic case is the case, then x dot is much smaller than 1. I remind you, our speed of light is equal to 1 by the choice of units. And so when velocities are much smaller, you can expand the square root and get mv squared divided by 2. Same thing here. When you expand, you get the constant term plus the famous constant term plus. Actually, if you fix the gauge from the very beginning, then the argument, you lose parametrization invariance, and variations will be difficult.
the parameterization invariance give no non-trivial concept quantity.
That's right. Yes. That's very important.
Is there any argument for this?
Oh well, argument for what?
That such a very general and very big class of invariance does not give
Yes.
any non-trivial information.
Yes. Well, it gives you a lot of information, but not in the form of conservation laws. I will try to answer the question. So, the usual symmetry, non-gauge symmetry, if you have the symmetry which is for which parameters are fixed, it leads, as we said, to conservation laws. Say some quantity q, and we derive the equation q dot equal to 0. Now, when you have stronger symmetry, which is coordinate dependent, when it's not that it gives no consequences. It gives you the consequence that q is equal to 0. And that's a stronger statement than q dot is equal to 0. So it's, for instance, you can define the energy in Einstein theory in such a way that you will see that you will separate matter and gravitational energy, and the Einstein equations simply say that the two cancel each other because of much stronger symmetry. But your question was very good. It's a type of questions you always have to ask yourself. Somewhat general questions of this type. Indeed, it seems that the stronger symmetry should give stronger relations, and it does. Okay. Now one more. We are not done yet with the variations. We can. And I must say, concerning your question, that as you probably heard, Einstein formulated his problems at the seminar where the great mathematicians like Hilbert and Felix Klein were present. And they started working immediately. And Hilbert was actually, there was a lot, even some unpleasantness between Hilbert and Einstein, but that's not my point. I'm not going to discuss this. The interesting thing is that even such super mathematician, the great genius like Hilbert, was confused about gauge symmetries and their consequences. Einstein was also confused. But Einstein's genius was that being confused, he wrote correct equations. Well, he first wrote, to be precise, he first wrote for several years, he was writing wrong equations and publishing wrong papers. It's very interesting to see how the struggle went. If you take his collected work, you see it firsthand. And but then, even not understanding full consequences of gauge symmetry, he found the right equations. And then, when you have the right equations, it's only a matter of time before you find the right interpretation of these equations. So it's a non-trivial question, indeed. Now I want to, I will rewrite in several different forms the variational principles, and you will see, we will establish now firmly the connection between mechanics and optics. And finally, we will see how it helps, apart from being very nice philosophically, it's a powerful tool for solving concrete problems. All right. So I remind you that we said that we can have the medium with the refraction index, which depends on x, and the time which takes, I will still call it s. This is actually, if you forget about, if you take imaginary time, this term is precisely this thing. In the case of light propagating through the medium, you have also some function here, the refraction index. This actually, if you translate it to the case of relativistic particle, this n is a special case of gravitational field. When light propagates in the gravitational field, it takes geodesic, it does not, the action n is, roughly speaking, gravitational potential. So, very crudely speaking. So it is, it has this interpretation, but that's not what I want to discuss. What I want to discuss is connection between this action and the action. This action, in this case, it was just time propagation for the light ray, and the action when the ordinary action for a particle. So we have this, and they look quite different, but they are related. So let's rewrite this expression, and I will now show you some tricks which are very useful and often used in modern physics. You will not find these tricks in any books, I think, but for sure in old classic books, there's no discussion like that. Let's introduce an auxiliary field and try to remove this square. This is a let me write it down as a square root. And I want to eliminate this square root somehow, because actually there are many reasons. Well, one of the reasons is that there's nothing like this square root here. But so consider another action which turns out to be totally equivalent to this one. You write down integral ds. I introduce a new field, a new variable h of s. Here we have, I will put n square of x of s dx over ds square. Let me write it down this way. Here we will divide it by h of s, and we add the term h of s. Very strange form of action. The meaning is that of it is that, well, first of all, you will see in 1 second that it is the same action as this one. But also, the h of s has a certain physical meaning. It's a one-dimensional gravitational field on the world line of this. Let me first ask you the question. So I introduce new variables. Our variables are now x of s and one more variable h. So we have, it's kind of an extra dimension which we are introducing here. One more independent variable, and we require that the action should be invariant under all variations, not only x of s, but also h of s. And now try to a semi-fair question to you. How this follows from this? The answer is simple. Remember, you have to vary everything. And you can, in your mind, vary, well, try to vary h, for instance, and see what happens. It's very simple. It doesn't require any algebra. So what will happen if you vary h? Okay, let's do it. What will be variation of this? I want to vary s, and I want to keep x intact at this point, but I want to vary this new auxiliary field h of s. So dictate to me the first term.
N squared.
The what?
N squared.
N squared remains here. I'm not touching x. So this is we are not varying x at this point. So this term, it was there, but we vary this term, so we get minus delta h divided by h squared, n squared dx ds squared plus delta h. And this must be equal to 0. So, what you conclude from this? It should
H squared
exactly h squared of s equals to actually h of s is equals to n of x of s dx ds. From this relation, you get the square. You can take a square root, of course. Now, when you substitute it back here, you take this value and you plug it in here, and you get, with the coefficient 2, you get this expression. So you see that, and then after that, you can vary x and obtain whatever you want. So this is the this is the expression for h of s. Well, I hope it is clear, yeah, that this term, for example, when you plug in h of s, you get precisely this thing. And this gives the same thing with, so all in all, you just have coefficient 2, which is irrelevant at this point, and exclusion of h, that's very important. It's simple but important to understand that you can have you can exclude some variables when you have variational problem. You can minimize with respect to some of them, not all of them, and use this equation. You plug it back into the original function. Well, again, what we are doing, since this procedure is important, when you have something new, you always should try to give some as simple and trivial example as possible. Suppose you have a function of two variables. And you first vary or extremize with respect to variable 1. That gives you the relation when x1 is some function of x2. Then you plug this relation back into this function. You get something which depends on x2 only. And now you can vary with respect to x2. And that will be the same as this procedure. So now we take partial with respect to x2. It has a slightly non-standard way of extremizing this function of two variables. What would be the standard way? How you find the extremum of the function of two variables? Well, you have to take all partials to 0. I leave it to you to check that this is the procedure number 1 which we follow. But another procedure is simply to solve two equations. And these two procedures are equivalent. This you have to work through yourself. But the outcome, the instruction which we get from this is that if it is convenient, you can easily minimize with respect to something and plug it back into the action. Okay. But we're still not done yet, although our action becomes very much, it starts looking like this one. It's not yet in this form. My goal is to match optics and mechanics, and the goal is not completed yet, is not fulfilled. But we are close. We are pretty close. So let's look now at this action. And although classically it's not much difference which action we work with, we are talking about concrete problems like you have a medium with position-dependent refraction index, and we want to know the light rays, the trajectories of light. And you can vary this thing and get some complicated equations, but we will see you can do a much easier thing also. Now this thing is invariant. Notice that this thing is invariant under reparametrization once again. Namely, let's look at the second term. We can replace h of s by df ds h of f of s. So that's what we get when we reparameterize. That's the transformation which leaves this second term invariant. But it also leaves the first term invariant. Because, again, it simply means this transformation law there is a, again, simple mnemonic rule. H transforms like 1 over ds. That's what it says. But then you see the number of ds here. We have here ds square, ds here, and 1 over h. So this thing is invariant. So my claim is that this functional is invariant under this transformation together with this transformation. The statement is that when you plug in x tilde and h tilde, you get the same answer. So we have this gauge symmetry once again here. But this time we can choose the gauge, and it is in our hand which gauge, which parameterization to choose. The functional doesn't depend on this. And before, when we looked at this form of the action, we choose the gauge s equals to t. But it's much more convenient here to choose the gauge h of s, in which h of s is equal to n square of x of s. If we choose this gauge, we find that's the, once again, when you have reparameterization invariance, there's infinite number of ways you can choose parameterization. And this one particular way in which you can do this. Here we used a different way, or a different gauge. All right, and then we get the action which must be equivalent to the original one. So we have the action dx ds square, n square disappeared from here, plus integral n square of x of s ds.
Why are we allowed to choose h of s?
Because you see, we can choose h of s to be any function. Once again, when we have reparameterization symmetry here, we can, the action doesn't change when you choose any function f. You can, so we can equate it. For example, another gauge which is completely meaningful is simply to set h to a constant. Because all you have to do when you are given the original gauge, all you have to do is to choose the function which bring such that h tilde is equal to a constant. That's one of the gauges.
So are all functions possible?
Well, you have to check subtle. There are some subtleties. Generally speaking, locally speaking, if you are not discussing the whole interval, but locally the answer is yes. But there are some subtleties which I will not go into. They are not relevant for these discussions. There are subtleties. Good people make mistakes with choice of gauge. You see, I'm discussing this way because it permeates modern physics. These gauge theories in all kind of problems you encounter with it, and same problems there are many. When you go to quantum theory, the things become really subtle, and you have to be very careful with gauge fixing. When we talk about classical, it's easier. It's pretty easy. And as you will see, very convenient. And you see, it's very strange and interesting statement that in one gauge you get this action. Without gauge fixing, you get this action. Now we can also get the third action by choosing there's a natural gauge, which is sometimes used, where h of s is equal to a constant. So you get integral ds n square of x of s dx ds square plus a constant. And variation, that constant is irrelevant because you can derive the equation from here. You see, you now very easily, by varying this thing, you derive various form of equation for the light ray. And how would you say, how would you put it? We will, suppose we solve the equation, Euler-Lagrange equation here, we solve Euler-Lagrange equation here. We get different solution. But what will be the difference? I'm not saying that when you have two gauges, the functions x of s will be identical here and here. They will be different. But they will describe the same physics. In what sense?
I have a question.
Yeah, go
Are
ahead.
the f's identical in the two? Like, does the f of s in the x transformation have to be the same as for the h?
Why?
Do the two f's have to be the same?
Oh, yes, of course. Because you see, you have this thing, and you want to, if you take a different f for x and for h, then those df ds, they certainly will not cancel here. So of course you can take here some different function f, but then the action will not be invariant under this transformation. So it is very important that df ds coming from here will cancel df ds coming from here. So it's important. And what I was saying actually was that these two solutions, we get some solution, let's say x first of s, by writing Euler-Lagrange here, and we get something else from here, and there are different functions, and I'm asking you a question, how they will be related, what do you think? Why I'm saying that they describe the same physics? No, it's because, you see, they will describe the same curve. They will be just two different parameterization of the same curve. That's the key point, that parameterization don't have to coincide. It's like I gave you this example as one of the first lecture. When you have a circle, you can write it down cosine theta x2 sine theta, but you also can write it down as a totally different function. So, for example, theta square. The functions are totally different, but they describe the same circle. And in this sense, all these actions which you obtain by different gauge fixing describe the same curve, the same trajectory of light ray, but differently differently parameterized. Okay, now what about relation of optics and mechanics? By this relation, I mean that the equations should be the same, and when the particle moves in a potential, somehow it should be the same as a function, as a light ray moving, related to the light ray moving in the medium where and we have to say, with to make it concrete, you have to answer the following question. You have to say, okay, there is analogy between optics and mechanics, but if I'm given a potential, what kind of refraction index it corresponds to? So, what kind of refraction index it corresponds to? Remember the you see, I choose the gauge, so it is the first term is very much like the kinetic energy. So what is the potential energy? Yeah, actually, the answer is the relation should be that n is square root of E. E is an arbitrary constant minus V of x. E is an arbitrary constant, but it turns out to be energy eventually. So you have this expression. In this case, n square E does not change the equation of motion. All actions are defined up to a constant. So you see, n square is basically minus potential energy plus something. So it means some practical advantage, because it means that you solve mechanical problem, you find the trajectories, and then you can interpret this solution as a solution for optical problem, the system of lenses and so on. And n square, moreover, it gives you a very simple way of, much simpler than other gauges. Good gauge usually simplifies matters. Maybe you can now tell me what is the fundamental equation of optics from this thing. I mean now not the action, but the equation of motion. Can you figure out what it is?
X double dot.
Yes. It's just yes. Then what on the right hand side? What? Yeah, it just should be a gradient. It's the Newton equation. It should be the gradient of the potential. N square is basically minus potential energy. So we get gradient d dx of n square. And that's the equation people really use when they discuss various optical systems. And actually, in a different form, this analogy between optics and mechanics appeared in the 19th century. It was invented by the Irish genius Hamilton. And it's, for me, it was very interesting to speculate like that if you take it very seriously, which didn't happen, then you can argue that there should be quantum mechanics, that classical mechanics is not the end, because that's what I'm saying is pure speculations. Or just, it's kind of fun to imagine what could have happened. So imagine you have optics. And in the 19th century, it was well known that there is wave optics. There are waves, there is diffraction. But in some approximation, you can describe it as geometrical optics, as motion of the infinitely thin light rays. But it was very well understood that geometrical optics is just an approximation to the exact result. The exact thing is the wave optics. So you have to take into account diffraction and interference of rays. And now it seems to be just one step to say the same thing about classical mechanics, that it corresponds to geometrical optics, but there should be some other mechanics, wave mechanics, which corresponds to wave optics. So you could have discover quantum, or at least foresee existence of quantum mechanics in the 19th century, which obviously didn't happen. And maybe it's too much to ask from human intellect. Anyway, that's for me, it was an interesting speculation. All right. So we see that rewriting things were not yet done with rewriting variation principle in different forms. And you will see in a moment that it is actually it is of great practical use. But we have to play around with these variational equations a little more. First of all, so what I'm going to do is to not to introduce new equations, but to introduce new equations equivalent to the old equations, but with some twist, and that will be very, very useful. Okay, so in the solution of the variational problem of mechanics, when we look at it requires it is all this form is also this term is actually fixed by symmetry, by Galilean symmetry, as we discussed before. But it describes what is called classical trajectories. Classical trajectory is a solution of the Newton equations of motion. And to fix the classical trajectory, you have to fix two things. What do you need to have a well-defined classical, a uniquely defined classical trajectory? What kind of data you need to be fixed? So when we have the Newton equation, there are infinitely many solutions, but to have a single particular solution, what should be fixed? Exactly. And so it is actually turns out to be extremely good idea to consider to introduce the concept of the phase space. Phase space is the space of you can define it as a space of classical trajectories. Namely, each trajectory corresponds to a particular point in this multidimensional space. The dimensionality is actually, since you have to fix two things here, the dimensionality is double dimensionality of the original space. You have to fix these two variables. And it is turns out once again to be very profitable to write down the action principle in the phase space, not in the configuration space. And I shall make it, again, we will derive it in full generality a little later, but at the moment let's do some very naive and simple exercise. What do we need? I want to introduce, basically I want to introduce variables in which I have to fix only initial positions, so the points, not the velocities. So let me perform the following trick. Let's compare it with the action of the following kind. Px dot minus so once again I'm introducing one extra variables. This variable it's different from what we did here. We introduce a new variable p, and I shall interpret xp as the phase space, which is very naive at this level, at this point, but we need to get some idea. So first of all, how we check why it is clear that this thing and this thing are equivalent. So let's suppose we start with this functional. How to get back to this one? It's the procedure which we followed in a different case in this lecture.
You can vary p.
Yes. What happens when you vary p? We want to exclude the p variable, then we hope to get this thing. So p variation of s. So once again, we don't touch x at this point. We take delta p x dot minus p divided by m dt, and this should be 0. From this thing, we have we clearly have x dot p equal to mx dot, and when we plug it back into this action, we get the first term gives you mx dot square, the second term gives you minus 1/2 mx dot square, and minus v. So we return to this action. Very naive thing. It is. We can more generally look at the actions of the type px dot minus h of p and x dt, where h is this thing. And now let's, before we go further, let's understand the meaning of this h. What can you say or guess? Let's calculate the energy related to this action. How shall we calculate? Always remember that calculation of energy is related to reparametrization of time. So when you have this action, give me a guess first what the energy will be. It will be h, and it is completely obvious by just looking at it. Why? Why the first term? the point is that the first term will not contribute to energy at all, and the second term will contribute h. As a result, h will be the conserved energy. So the first question is why, when we reparameterize with this first term, p of t dx t dt, why it is not contributing to energy?
P dot equals 0.
No, p dot is not equal 0. P can change. So what we are supposed to do, remember general rules. They are the same all again and again. We take new variable, and we calculate p tilde x dot tilde and compare it with this thing. Actually, if you remember my mnemonic rule, which I gave you before, the mnemonic rule count the number of dt's. How about the number of dt's in this case? Yeah, it is parametrically invariant. Actually, well, first of all, this number of dt's, dt here and dt here, they cancel. That gives you the idea why it is. Now we take p dot, p, the new action is p of f of t, d dt of x of f of t, integral over dt, and it's equal to p of f d df x of f integral over df. So it's the same functional. It's parametrically. It's another parametrically invariant functional, this px dot. Therefore, when we look at the coefficient in front of a dot, when we write down f as t plus a of t and look at the coefficient in front of a dot, this term will not contribute. It will simply be independent of a of t. While the second term, it will contribute, and it's quite obvious what it will contribute. It has dt in the numerator, so it will be h dt df, and it will be just ha dot dt. So the h here will it was not a coincidence that we got here the sum of kinetic and potential energy. It's only in very special systems you can separate kinetic and potential energy. Generally, it's some function of p and x, and it's not, does not really split into these two pieces. But in any case, in all cases, it is just the energy because of this argument. Well, now we are ready to, so we can safely replace this thing, and now we can, by more general action, and we will generalize even this. And the question here is that what kind of data so let's write down integral px dot minus h of p and x dt. And this is the action in the phase space. Phase space again, I'm not giving a definition yet. I'm giving an example at this point only, and we will define it a little later. It's a space of P of t and x of t, and trajectory is defined if you fix what in terms of p and x. Yeah, only starting point. You don't have to fix derivatives, and that's because we have this functional, which, well, let me first do the trivial part. So let's vary p. We get delta p x dot minus dh dp. And vary x, we have p delta x dot minus dh dx. Here you have to integrate it by parts, and you get x dot plus dh, p dot, excuse me, p dot plus dh dx delta x. So you have two equations. The equation one is x dot is dh dp. The equation two is p dot minus dh dx. This minus is extremely important. Actually, we will see it a little later, if you have a plus here, this gives you the equation not derivable from the variational principle. It is very, as I said before, derivability from the variational principle is highly non-trivial fact, and it's only in this form it's preserved. And you see that how we see immediately that it's the equation in the phase space. If you have in order to fix a solution, you have to fix only x0 and p0. How to see this? That's the last point for today. How to see that it's enough data to find the trajectory at least nearby. Well, we can always look at when we have the trajectory. We can always Taylor expand it. And the same thing here. And the point is that the point which I want you to appreciate and to explain that all these series are all these coefficients are fixed, provided that you fix this one, the initial data. Why is that? That's right. When you have these guys, I'll give you a concrete expression for all these guys. These guys are trivial. You simply take a given Hamiltonian and you plug in dh dp here and minus dh dx here. So these terms are obviously, you found these terms. And here you take it at the initial moment. A slightly less trivial, but really the last point, how you determine x double dot and p double dot in Taylor expansion. What you have to do? Differentiate, right. If you differentiate it with respect to t and set t to 0, you will find this thing, and recursively you will find everything. Of course, this series can diverge at some point, and that's a much much less trivial question, but locally, in the vicinity, it explains you the difference. Okay, let's stop here. We're getting late.